So in this video we'll be seeing how to unhook the DLL from our process. So unhooking means the EDR will generally place the hooks at the function beginning to capture the parameters. So those are the functions will be in the text section. So if you go to exports, you can see the function related to virtual offsets. So these 94380, so that will be inside the text section. So virtual address starts from 1000 and virtual size is this one. So the offsets will be inside the text section. So the functions will be inside the text section, and these EDR places the hooks at this starting of the functions. So what we are going to do is we are going to replace the entire text section with the legitimate text section. So we have this empty DLL.dll. So on the disk the DLL will be clean and no hooks will be placed in the disk empty DLL file. So we are going to read the contents of the empty DLL from the disk and copy into our own process. So that's what we are going to do in this video. So I have written the PE parser, parse from file. We need to say the file. Let's say this as disk DLL. Now on the disk we need to read the section headers and the raw address. So the raw address is the raw offset from the file. So after 1000 hexadecimal bytes from the starting file byte, you will have this text section until the 12E1000. So that is the raw size. We don't need to copy the entire raw size, we need to copy the virtual size. So this virtual size may be less than or equal to raw size. So these this happens when we have non-initialized variables or like dynamic arrays. So the virtual size will be less, and also this raw size can contain the null bytes at the end of the section because of the file alignment. So that's why the raw size is greater than virtual size. So what we are going to do is we are going to read from this raw offset the virtual size number of bytes and place that in the buffer so that we can copy later. So we have the disk DLL. So let disk sections is equals to disk DLL dot get sections. So these are the section headers. So I have written this PE parser, so you can actually parse the PE file, or you can use this PE parser library. I will be given in this description. So for I in 0.disk sections dot length, now we are going to loop all over these text all of these sections and find if the name is text section, then we are going to copy the bytes. So generally the first section will be the text. In case for safe side, we are going to parse the section name. So let section name is equals to read string from memory, or we can say this as let proc handle is equals to get current process. So why we are doing this is we can pass the process handle of another process. So this can be useful for unhooking the DLL in the remote process. disk sections of I dot name dot trim and matches. We are removing any null bytes because the length of this section name is 8 bytes by default. So the dot text section, the dot text occupies 5 bytes, so the remaining 3 bytes will be 0. So that's why we are going to trim that one. So we have got the section name. If section name is equals to dot text section, then that means we are going to read the at this offset, raw address offset, the virtual size number of bytes. Okay, so let mute original text. So original text means the original text section, the cleaned version. So read process memory and process handle, and the base address is, we have the file contents, and the file contents are stored in the structure member file contents, and if we are parsing from memory, the contents are stored in memory contents. So disk sections, disk DLL dot file contents dot as pointer. So that is our starting file buffer as usize plus disk sections of I dot pointer to raw data as usize as constant c void. So we are going to read from the file starting address to add the pointer to raw data, that is this raw address. From there onwards we are going to read the virtual size amount of bytes. LP buffer we can actually do like this: original text is equals to vector of disk sections of I dot misc dot virtual size. As usize. Okay, we are good to go. LP buffer original text dot as mute pointer and original text dot length. So I think we are good to go. We can go and print the contents of this original text. So these are the contents. So let's go and print the 9th byte of this. 9th byte should be, sorry, should be 14 hexadecimal. So you can see the 40. So now we have the buffer that contains the clean version of NTDLL. Now we need to parse our own process and replace the NTDLL text section with our buffer. So we need to find the DLL base address. We can say get loaded modules, get current process ID. So this gives us the DLL base addresses. Let DLS is equals to so we will be using create to help 32 snapshot function to retrieve all the modules. So we will be looping all over these modules and appending to the dictionary. We can also use the NT query information process function as well. So we have the DLLs for if is equals to NTDLL.DLL, then let's DLL base is equals to 0, DLL base is equals to star v. So if the DLL is NTDLL, then store the DLL base address in this variable DLL base. Okay, now we have the DLL base. We are going to parse this as a PE again. PE parser, parse from memory and the process handle and DLL base. So what we are going to do is we are going to parse this NTDLL which is in the memory of our process as a PE file to retrieve these section values. Let PE is equals to so now we are going to loop over these sections and copy the text section. So let memory sections is equals to PE dot get section headers for I in 0 dot dot memory sections dot length. So we can copy this line, paste here. If section name is equals to dot text section, so now we have this text section information. We need to read the virtual address. So at this DLL base plus this virtual address, we need to write the contents. So write process memory and the base address is DLL base plus memory sections of I dot virtual address as usize and the buffer original text dot as pointer as constant c void and how many bytes we want to write, that is original text dot length. So before writing this, we need to change the memory protections from this address, virtual protect x and size is original text dot length. New protection is page read write, and save this old protection in a variable. And after writing the content, we can just copy this function again, and now we are going to restore the contents, protection, old protection. So I think we are good to go. So I have changed this memory protection to page read write execute, and I think now there are no errors. So if I change back to page read write, then we are getting some errors because the text section should be executable. Okay, so my bad. So we have written successfully the cleaned version of NTDLL. We can verify that by reading from this address again. So we have written to this address DLL base plus virtual address, so we can try to read the contents from that location again. So copy this location, let's say let mute previous text, let's say new text. And the buffer is new text dot as mute pointer, mute c void, okay. Now let's go and print the 9th byte. So it should be same as this value 40. Now you can see the same value. So that's how you can unhook the DLL from the disk. And there is one important thing, that are the base relocations. So you can see here the base relocations, the page RVA. If you go to this page RVA, and there are the entries. So this entire block is a base relocation table, and the first 8 bytes tells us about how many entries. So the first 4 bytes tells us the page relative offset. So if you add the PE base address to this page RVA, you will get to the values where you need to relocate these hard-coded addresses. So I am here at this 132,000 page RVA, and you can see the offset from the page. So that is 8 bytes, and relocation RVA is, you need to add the 8 to this page RVA. You will get the final address where you need to read the contents of these hard-coded values and add the delta value to this. So what is this delta is? In the optional header you can see the image base is 18 crores or something. So not every time the the PE file gets loaded at this base address, so it might get loaded at the 20 crores. So what you need to do is you need to subtract the loaded base address minus the preferred base address. So this is the preferred base address. You need to subtract this new base address minus this preferred base address. You will get the delta value. So that is the difference, the delta value, and you need to read the 8 bytes from this address and add this delta value to this and write the new value at this address. So that's how you fix the base relocations. So I have already written to enumerate the base relocations. So it will return a dictionary of this page RVA and the offsets. So here you can see the values A008, A018. So A stands for the 64-bit. So you need to cut off the first 4 bytes, 4 bits from these 2 bytes. So the remaining 12 bits constitutes of the offset from the page. So you can see the A008 and 8, A018 and 18. So you need to cut off these first 4 bits and check if that value is A or not. If it's A, then it's 64-bit. So the most of the times we are dealing with 64-bit executables, it will be A. So from here onwards, let's go and retrieve the base relocations. So we already have this PE structure object. So PE dot get base relocations. Let's go and print this. So these are all the base relocations. So you need to add the DLL base address to this page RVA and also add this offset. And finally, you after adding all 3 values, you get an address. Read the contents at that address and update the delta value and write that newly gotten value into this address. So let's go and do that. So let's calculate delta is equals to the DLL base address we have retrieved from previous function. So our NTDLL base is located at some address. We need to subtract with this PE dot get NT header dot optional header dot image base. So you will get this delta value. So go to this optional header and image base. This is the preferred image base. Now there is one important thing. You don't need to overwrite all the base relocations. So already the base relocations have been done by the Windows loader. What we need to do is we need to overwrite the values that belongs to the text section only. Why? Because we have only replaced the contents of the text section. So that means whatever the hard coded values are in the text section needs to be relocated. So you need to see the page RVA. This is 132,000. So if we go to the section headers, the starting is 1000 virtual address and the ending is 12 something. So 132,000 is greater than this virtual size if we add to this one virtual address. So 132,000 is somewhere belongs to this RT section. So that means you don't need to base relocate these entries. And same for the second page RVA. This is 133,000 and this does not belong to the text section. So you can see the virtual address is 1000 and virtual size is only 12,000 or something. So the 133,000 comes after this hard data. So that means you no need to relocate those entries. So you need to add a check to see if this page RVA is inbound between this virtual address and virtual size. So let's go and do that. For page RVA comma offset in ampersand base relocations of I. So we have this page RVA. If page RVA as usize greater than or equal to, so if this page RVA is greater than or equal to virtual address plus virtual size, so that gives us the last address of this text section. So we need the text section values here. So let's say let mute text section is equals to so we are going to copy the values contents of this, copy the contents of this text section into separate variables, so we can compare the virtual address and virtual size here. So text or page RVA as usize. There is another condition. So the first condition is if its page RVA is greater than this one, and if its second condition is page RVA is less than this virtual address, is less than text section dot virtual address. Then what we are going to do is we are going to continue. Let's look at the condition again. Page RVA greater than virtual address plus virtual size, and the page RVA less than virtual address. Okay, we are good to go. So that means this page RVA is not inside this text section. Okay, if the page RVA is inside this section, then that means we need to relocate these entries. So first we are going to read the 8 bytes from the DLL base address plus page RVA plus offset. Let mute old value is equals to 0, read process memory, and DLL base plus page RVA as usize plus offset as usize, and the buffer. So this is a vector of U8 bytes, 8 bytes. We are going to read 8 bytes into this old value buffer. So we need to convert this old value buffer to the integer. Try into dot unwrap. So this will try to convert the buffer into U64. So we have the old value. Go to this and go to the relocation RVS. So these are the 8 bytes. For example, we have read from this address these 8 bytes. We need to add the delta to this value and write the new value at this address only. So let new value is equals to old value plus delta, and write this new value at this same address. So same address, copy the same, new value dot 2 any bytes. So we are converting that U64 8 bytes value into buffer. So I think we are good to go. So we have successfully relocated the hard-coded entries. So let's go and run this. We should not see any errors. So we are good to go. So that's how you can unhook the DLL from memory by reading the clean DLL from the disk and copying the contents of text section into our process. So here we have read from the file, so read from the disk. You can also host this NTDLL in our payload server and retrieve. You can do a HTTP request to retrieve the contents of NTDLL, and you can parse from the memory and also do the same process. Just retrieving the contents can also be done from HTTP or any payload server, web server. So that's all for this video. We have seen how to overwrite the text section from the clean version of DLL and also fix the base relocations. In the text section we just replace it.